Swayam Prabha. Digital India. Educated India.
Welcome back. So, in the last lecture we stopped here. So, basically we were discussing about the Mohr Coulomb failure criteria. So, there we had seen that the failure is not happening at the maximum normal stress or at the maximum shear stress, rather failure is happening some critical combination of shear stress and normal stress, which is nothing but this point D. So, which is nothing but this point D. So, point D is telling about the failure, right. So, therefore, the angle, I mean if you recall your Mohr circle representation. So, basically the angle between the major principal stress and the failure plane. So, therefore, the failure plane, I mean if you consider the pole method, the failure plane will be making an angle say theta, because 2 theta is the angle in the stress field, that is nothing but in the Mohr circle representation. So, if you talk about the physical plane, so this is your physical plane, in that physical plane basically that will be I mean coming as theta only, right, half of that angle. So, 2 theta is the angle between the major principal plane and the failure plane, right, because this is your failure point, this is your major principal stress point. So, this is the angle 2 theta is the angle between major principal plane and the failure plane, and that is shown in the physical plane like this theta. So, theta is the angle between the, so this EF is your failure plane, right, which is making an angle theta with the major principal plane. Okay. So, I hope you have understood this concept. So, now whatever you have understood now, so that thing we are going to represent in the mathematical expression. Now, the radial line, AB. So, this radial line AB defines the major principal plane, agreed. So, I mean if you recall your Mohr circle representation, whatever you have learnt in your say mechanics, right. So, the radial line AB defines the major principal plane CD, okay. CD means whatever we have seen in the physical plane, and the radial line AD. So, this is the radial line, and this radial line AD defines the failure plane EF, okay, agreed. Okay. Now, it can be shown that angle BAD, angle BAD, so BAD, angle BAD is equal to 2 theta, which is nothing but equal to 90 degree plus phi prime. Now, why it is 90 degree phi prime? Because this angle is 90 degree, this is the radial line and this is the tangential line. So, this failure envelope is a tangential line. So, therefore, this angle is 90 degree. So, this angle is 90 degree, this angle is say phi prime. So, therefore, this angle will be 90 degree plus phi prime, which is nothing but equal to 2 theta. So, this we have got. Now, there from this I can write theta is equal to 45 degree plus phi by 2, right, phi prime by 2, right. Now, what we are getting here, now AD by FA, right. So, again AD by FA is equal to sin phi prime, right. So, AD by FA. So, this by this, because this is a I mean this angle is 90 degree, right. So, AD by FA is equal to sin phi. So, this angle is phi. Now, FA is equal to, now you see this FA is equal to FO plus OA. Okay. So, FO plus OA is equal to, what is FO? FO is nothing but C prime cot phi. So, this angle is phi, this is C prime, okay. So, C prime cot phi plus sigma 1 plus sigma 3 by 2. What is sigma 3? this is your sigma 3, from O E is your sigma 3, similarly O B is your sigma 1. So, sigma 1 plus sigma 3 by 2, which will be nothing but O A, agreed. Okay. Now, again we can write A D. What is A D? A D is nothing but the radius of the Mohr circle, that is nothing but sigma 1 minus sigma 3 by 2. Okay. So, sigma, the radius of the Mohr circle will be sigma 1, that is the major principal stress, minus the minor principal stress divided by 2, that will be your radius. Now, once you know all those things like F A, A D and all those things, so you put in the expression of sin phi. So, sin phi, what sin phi is? Sin phi is equal to A D divided by F A. So, in place of F A I can write this, in place of A D I can write this. So, that comes like this. Okay. Now, from this if you try to simplify this thing, this equation, then you will be getting sigma 1 is equal to sigma 3 1 plus sin phi divided by 1 minus sin phi plus 2 c into c cos phi divided by 1 minus sin phi. I am not talking about the prime all the times, because prime is written. So, it is quite understood that these parameters are effective parameters. So, all the times I am not talking about the prime, sigma prime, c prime, phi prime. So, I am skipping those things. However, that is already accepted that these parameters are effective parameters. Anyway, so equation 5.8 is giving me the relation between the major principal stress and the minor principal stress, along with the C, that is the cohesion, and phi, that is the angle of internal friction. So, now 1 plus sin phi by 1 minus sin phi, mathematically I can express tan square 45 degree plus phi by 2, which is nothing but equal to tan square alpha. So, alpha stands for 45 plus phi by 2. Okay. In place of 45 plus phi by 2, I am writing alpha. Okay. So, that is nothing but tan square alpha. Similarly, cos phi by 1 minus sin phi, I can write mathematically, that is nothing but tan 45 plus phi by 2, which is nothing but the tan alpha. Therefore, the relation whatever we have got in equation 5.8 becomes sigma 1 is equal to sigma 3 tan square alpha plus 2 c tan alpha. So, this is the relation. So, this is your Mohr Coulomb failure criteria. So, Mohr Coulomb failure criteria says that is nothing but sigma 1 plus sigma 3 tan square, sigma 1 is equal to sigma 3 tan square alpha plus 2 c tan alpha. Now, we will be talking about the laboratory experiments available to determine these parameters, okay, like C and phi. If you, so therefore, what you get from this equation? So, if you know C, that is the cohesion, and the angle of internal friction phi. So, if you know these two parameters, basically you can calculate, and of course, if you know the sigma 1 or sigma 3, you can calculate the other parameters. At the same time, if you know C and phi, you can establish the Mohr Coulomb failure criteria, and then whatever stress you are choosing, you can say whether this stress is coming below the failure criteria or coming just on the failure line, or it is not feasible. So, this kind of say concept, or this kind of say idea you will be getting from this once you establish the failure criteria. Now, the laboratory test for determination of shear strength parameters. So, first we will discuss about direct shear test. So, what we do here? So, basically here you will be having two halves. So, this is the top half, this is the bottom half of the shear box. So, this is known as shear box. Okay. Now, you will fill the sand. So, this is filled with sand. You will fill the sand in that particular mold. So, this is a kind of mold which will be having two halves. Okay. So, this is your top half, this is your bottom half, and this is the mold. Inside the mold you will be filling the sand, for which not sand, for any kind of material, for which you want to find out the shear strength parameters like C and phi. So, if I talk shear strength parameters, that means C and phi will be counted as shear strength parameters. Okay. So, I want to find out the parameters. Now, on top of the sand porous stone to get the pore water pressure dissipated from the soil body. Similarly, you will put another say porous stone at the bottom, the function is same, it will try to dissipate the water from the soil body. Okay. So, there is no, I mean the things will be completely effective, right. So, because you are not allowing any kind of pore water pressure building up in the soil matrix. Okay. Now, what you are applying, what you are doing. So, these are two porous stones. Now, you are applying normal force, okay. By some means or by some say mechanism, you are applying some normal force on the which will be developing the normal stress, right, because this normal force you are once you are applying. So, along that plane basically, or any plane if you consider, along that plane if you divide the plane area, then you will be getting the normal stress acting on that particular plane. Okay. Now, you are shearing, now you are applying some shear movement along this direction, and the one top half will be moving, okay, with respect to the bottom half. So, basically this is something like this is the mold now. So, one half is allowed to move over the other half, okay. So, basically you will be getting this kind of movement, that means you are shearing the soil. So, the shearing is happening at that plane, and slowly you will be getting some shear force, okay, or the shear stress is getting developed along that plane, and at certain point you will be getting the failure. So, that means the combination of normal stress due to this, I mean, so this is fixed for the whole experiment. So, you are applying one normal force and you are executing the complete shearing, that means complete failure. So, that means you are getting the combination of sigma and tau for a failure. Then similarly, you will be increasing the normal force, okay, and then again you will shear it, you will go to the failure, then you will be getting another combination of sigma and tau for which you are getting the failure, and so on you will be going on. So, you will be increasing sigma and you will be finding out the failure, I mean shear stress required for failure, right. So, in that way you will be getting different combinations of sigma and tau, and then you plot that thing, and then you, I mean these points basically this combination, if you plot in sigma and tau space, basically these points will be coming in sigma and tau space, and then if you join that thing with a straight line, that will be giving you the failure envelope, Mohr Coulomb failure envelope, right. So, the idea is like that. So, once you know the Mohr Coulomb failure criteria or the failure envelope, from there you can find out C and phi. Okay. So, now let us see how we can extract the, or how we can interpret the results obtained from this direct shear test. The soil specimen may be square or circular in plan. So, the box, whatever mold I told you, that mold could be in could be circular or square in cross section. The size of the specimen is 51 millimeter by 51 millimeter by 25 millimeter. I mean two kinds, I mean two types or two sizes are available. The first one is 51 by 51 by 25 millimeter, another one is 102 by 102 by 25 millimeter. Okay. So, sometimes you need the smaller specimen, sometimes I mean depending on the soil gradation you need say bigger size or bigger mold. Now, shear force is applied by moving one half of the box related to the other, as I told you, right. The bottom part will be moving, and the top, I mean bottom part will be there and the top part will be there. So, basically you will be getting the relative movement. So, one part will be fixed, another part will be shearing. So, I mean another part will be sliding over the other part. So, in that way basically you will be getting the shear force which will be developed at the interface or at the plane of the separation. The shear test can be either stress controlled or strain controlled. Now, what do you understand by stress controlled and strain controlled? Now, we will come to that point. Now, before that, if you use dense sand and if you use loose sand, now at this point you are quite familiar to these terms dense sand, loose sand. It depends on the relative density, right. So, already we covered this thing. So, based on that we can say okay, this is my dense sand, this is my loose sand. Now, if you try to find out the shear stress versus shear displacement relation in dense sand and loose sand, basically you will be getting the relation like that. For dense sand, it is first it will increase, it will reach the peak and then it will fall and it will be becoming constant, almost constant, right. Whereas, in case of loose sand, it will be monotonously or continuously increasing and it will reach the constant part or the ultimate part. So, basically at the ultimate state, okay, both dense sand and loose sand is giving you the same shear strength. Okay. However, the peak shear strength for dense sand is much more higher than the peak shear strength of the loose sand. Okay. So, another thing you can conclude from this, the peak shear strength and the ultimate shear strength both are almost same for the loose sand, whereas the peak shear strength is much more higher than the ultimate shear strength for dense sand, right. So, that you are this is for a constant normal test. So, that means what you are doing basically, you are applying some normal force as I told you, and you keep that thing constant, and then you are gradually shearing it. So, in the process of shearing, you can develop this kind of these curves you are getting developed when you are shearing. So, gradually the shear resistance or the shear stress is increasing with the shear displacement, and it will be reaching reaching at the peak, that is for dense sand, and then it will fall down, right. Similarly, for loose sand it will be continuously increasing and it will be becoming constant, right. Okay. Now, what is happening in case of change in height of specimen? That means, so you have the height of the specimen as 25 millimeter, right, as you have seen, that is the mold depth, right. So, change in height of the specimen. So, that is happening because of this two types of sand you are using, dense sand and loose sand. So, as you progress the shear displacement, as you are applying the shear force, that means gradually the shear displacement is happening, okay, in the mold. So, basically the dense sand will exhibit some amount of reduction or the compression in the volume initially, and that means the material will be compressed and then it will dilate, it will expand, and this expansion is shown like that. Whereas, in case of loose sand, it is always compression, that means the volume, whatever volume you consider initially, as you are shearing it, the volume will be getting reduced. Whereas, in case of dense sand, initially it will be getting reduced and then it will be increased, right. So, that is happening in dense sand. So, this with shear displacement, this is the change in height of the specimen happening in the experiment. Now, as we told about stress control test or the strain control. Now, what are these tests? Now, in stress control tests, the shear force is applied in equal increments until the specimen fails. Okay. So, what you are doing here? So, you are in case of stress controlled, your normal stress is constant, right. Now, you are applying say delta amount of shear stress and you are waiting for some time, then you are increasing 2 delta amount of shear stress, then you are waiting, then 3 delta, then 4 delta, and so on, you are going on increasing. That means, you are controlling the stress, right. So, first you have applied delta amount, delta tau, then say 2 delta tau, then 3 delta tau, 4 delta tau, and gradually you are increasing the shear stress and ultimately you will be getting the failure, right. So, that is known as stress control. So, here actually you are controlling the stress, whereas in case of strain control test, a constant rate of shear displacement is applied to 1/2 to the shear box. That means, here actually what you are doing, you are applying constant, that means your shear displacement, that is the rate, because you are applying the shear movement, that is shear displacement, that rate of shear displacement is constant. So, at the constant rate you are shearing the material, right. That means, you are controlling the strain, that means the shear displacement you are controlling, you are not controlling the shear stress, okay, and you are going to the failure. So, these two things are happening. You can have two options, either you go for stress control test or strain control test, depending on the requirement. Okay. Now, the advantage of strain control test is that in the case of dense sand, peak shear resistance that is at failure as well as lesser shear resistance that is at a point after failure called ultimate strain can be observed and plotted. Now, what does it mean, right? Now, if you look at this is your shear stress versus your displacement, shear displacement you plotted, right, and in case of dense sand you got like that, right. Do you remember? Just now we have seen. Now, in case of stress control test, what you are controlling? You are controlling stress. Now, you are controlling stress means first you are applying delta sigma, delta tau say, okay. Then in the next increment you are going for 2 delta tau and gradually you are increasing, okay, and you are reaching say this peak. Okay. So, what you are doing? You are gradually increasing the shear stress, that is a stress control test you are performing. Okay. In the stress control test, once you reach the peak, then further this part from this point to this point, this part you cannot capture, because now this part cannot happen with the increase of stress. Have you understood this thing? So, this rising part you can capture by increasing the stress with similar increment or the same increment. That means, you are controlling the stress and you are getting that. Once you reach the peak, this falling part you cannot control with the increase in stress, right. So, now this point, from this point to this point you cannot increase the stress, rather stress is decreasing, right, strain is increasing, right, the displacement is going on increasing, but your stress is decreasing. So, this falling part you will not be able to capture by stress control test, whereas the same thing if you do that, with strain control test. Now, what is happening you see, in strain control test you are controlling the displacement, the rate of displacement is constant. So, this is your constant displacement you are considering, you are going on in, right. So, continuously you are increasing the displacement, right, there is no issue. So, if you continuously increase the displacement, you will be able to capture the whole curve, right, whatever was not possible in case of stress control test. In case of strain control test, now you are able to capture the whole plot or the whole portion, right, of the stress strain curve, right. So, that is why this is written. The advantage of strain control test is that in the case of dense sand, peak shear resistance that is at failure, that is here, as well as the lesser shear resistance at a point after failure, that is called at ultimate, that is here, right, can be observed and plotted in case of strain control. But in case of stress control, you cannot go, this part is not possible for your stress control test. Okay. So, I will stop here today. So, in the next lecture we will be saying or we will be discussing the direct shear test in more detail, and we will be finding out the equations, okay, applicable to the direct shear test, and then we will move further with different other kind of say laboratory tests. Thank you very much.